So, welcome everyone. Welcome to this lecture of digital system design. So 2 weeks ago I started with the topic of formal verification of hardware designs, and this is the lecture I want to finish today. And then afterwards want to have a question hour regarding the practicals, and this we will do this on Discord, so we can chat privately or talk privately about your designs. Yeah. All right. So regarding formal verification of hardware designs. So 2 weeks ago I stopped in the middle of the lecture. So today I want to continue with and start with the first Hello World example. So for formal for the formal verification of hardware designs, you write your hardware, and then what you do is you also write your specification. This is done here in this formal block, and in this example we have two statements for the formal specification. The first one is that we assume that the counter never reaches 10. This is something we can assume about this design, about how this module is driven from the outside, but we can assume that this counter will never reach 10. And when we have this assumption, then we have an assert statement. We assert that the counter never reaches 50. Since the counter only increments by 1 or performs a reset, we can, for example, look at the code and come to the same conclusion. But what we can do is we can give this to a solver and get a mathematical proof out of that, saying that the specification is fulfilled. And to do that, we can use, for example, Yossi's SMT-BMC. And for that we have to write a small configuration script. Basically, we tell the program which solver we want to have, which mode is used for verification. In this case it's K-induction with a step with step amount of 10. We have to specify all the files which we want to verify, and then we have a small script basically which is used for Yossi's to parse the files. All right. And when we run this using Symbiosis, it basically creates a hello world, a hello world directory, a hello directory here that contains all the files. So it copies all the files into it. So the output directory basically contains everything necessary to run the proof again. In this case we have one engine. It is SMT-BMC set 3, and it runs two independent proofs. So the first one is the bounded model check, and the second proof is the K-induction step. Both of those proofs, they independently return a pass, which means that the whole proof is correct, and the design is proven to be correct according to our specification, of course. Alright, so let's look at the keywords, at the Verilog keywords, which you can use to create our specification. So we already saw two statements before. We saw the assume statement and the assert statement. So assert means that we have a bad state, or the statement we describe with an assert is a bad state. So if this is violated, we have a bad state. You maybe know that from programming languages like C, where you can also write assertions in your C programming code. Assume means that if this expression in the assume statement is false, the solver does not consider the state at all. We act like the state does not exist, so we can restrict the number of states or the number of valid states for a design. And restrict in verification has the same meaning as assume, but in simulation they are a little bit different. In simulation, if an assumption is violated, then this is an error. And in simulation, if a restriction is violated, then it is just ignored. So the question is sometimes when to use what. So there's a simple rule of thumb. If an assertion depends on an assumption, and it would be possible that the assertions are violated if the assumptions are violated, then you should use assume. But in some cases, you would like to make the proof simpler by not considering certain states. And in this case, you should use the restrict keyword. But if you want to be on the safe side, then you would use assume. So there are also some fairness and liveness properties which can be verified. So there is a statement or a keyword s underscore eventually, and this can be used in assumptions and assertions. This keyword says in the first statement is if some requirement, and then assume with s eventually means that we assume that the signal response is either true in the current cycle or in any future cycle. So there might be an arbitrary number of clock cycles in between. But the circuit is bound to eventually reach a state where response is high. And the same thing can also be done for assertions. So you can assert that either in the current cycle or in any later cycle, the response goes high. This can be used, for example, when you want to assert that a finished signal goes high and in a later clock step. So you start the computation with, for example, triggering a start signal, and then you assert that with s eventually, of course, then you assert that the finished signal goes high in a later clock cycle. This can be used to verify that, for example, the computation of your circuit finishes. Yeah. The only thing is that those two properties, fairness and liveness, they can only be used with Eiger-based flow, so you cannot use simple k-induction proofs for that, so you have to use the more complex Eiger-based flows for that. Alright. So what are other keywords? So sometimes it's quite useful to have some free variables in your proof without the need of adding new primary inputs. So primary inputs are by definition free inputs. So to create a free variable, you could in your design you can, for example, route this signal back to the top module, and then you have free variable for that signal. But this is very cumbersome because you have to change your design just for the specification of your proof. and if this signal you want to have a free variable for is very deep in your design, then you have to make a lot of changes. So in Yosys you can use the Verilog command any sequence for that. It just creates a free variable. You can also use the keyword anyconst. That is also a free variable, a primary input that is latched in the first cycle. So it means that it is an arbitrary number, but it is constant for the whole proof. There are similar things, similar statements in system Verilog. You can declare, for example, a rec as rand or rand const to have those kind of free variables. However, they cannot be used for arbitrary signals in blocks. They have to be in so-called checker and end checker blocks. But Yosys is not that strict here, so they can in Yosys rand and rand const can be used in for all everywhere, not just in this checker and end checker blocks. All right. So let's now look at a more complex example. So this here is a Fibonacci number generator. It has some control inputs. There's a pause and start signal. There is there is a main block which is surrounded with if not pause. We have a start signal telling the circuit to start a new computation. We have n to compute the nth Fibonacci number as an input, and we have also some control outputs, busy and done. Busy is high while the Fibonacci number is generating the numbers, and finish is high in the one cycle where the output f holds the number we wanted to compute. We have an initial condition. So we have an initial condition telling that done and busy are 0, and then internally we have also some housekeeping variables for creating the numbers. Yeah. All right. So in the always block, we are basically, when we've started, or when we start, we reset our numbers, and then eventually we are computing our Fibonacci numbers and also counting, incrementing a counter to know at which step we are currently. All right. Okay. So when we look at that circuit, you will see that there are many things to care about. One thing, for example, is that the counter, or the end counter n, the number of Fibonacci numbers we want to compute, is not sampled. So n is directly taken from the input. So one assumption on that is that that n must be stable for the whole computation. If n changes over time during the Fibonacci generator is computing its numbers, then we would count to a different number. All right. So for that Fibonacci number, we want to make a specification. So this is shown on the right. Again, this is put into this if-def formal, which is only considered when being in the formal mode and parsing the parsing the specification by the solver. All right. So what is the specification here? So one part of the specification is regarding the start signal or when being busy. So there is a specification telling when we are busy, we do not assert start again. This is something we can assume from the outset. So when we are busy, we will not trigger start again. The second part here is that when we are busy, we keep the input signal N stable. We will not change it. So this is one thing we can assume on this circuit, on the outsides of the circuit, on who is driving the circuit. And then we will assert the behavior of the Fibonacci number generator. We say when we are done, so when we finished, then we want to assert behavior. All right. So we assert when f for the case 0, we assert that the Fibonacci number is 1. When it's 1, the Fibonacci is again 1. When 2, it's 2. When 3, it's 3. When 4, it's 5, and so on. So this is the Fibonacci number sequence. You observe that here we have we take the past value of n. The reason for that is that when done is high, we could always the system could always already trigger a new computation, so it could start with a new value, and n would be then different. So you need to take the value of n one cycle before. That's why there is a past. So this is the part where we asserting the behavior the behavior of the Fibonacci number generator. And then there are so-called cover statements here in the second part. So these cover statements, they essentially say when we are doing simulation, we are interested in seeing those cases. We are interested in seeing a behavior such that f equals 13, or f equals 144, or the past value of n was 15. So then this basically creates you a behavior or a combination of signals on how to drive the circuit such that these cover statements are fulfilled. And then when we start the circuit, so when start is active and pause is not active in the same cycle, then eventually we will see the done signal going high at the later cycle. So this is fairness as liveness, as we've discussed, as I've discussed before. All right. So this is the Fibonacci example. So with this you get two different symbiosis configuration files. One is proving that the assertions under the assumptions we specified. And in this case it's using a different solver, it's using ABC PDR as the engine. Then we have a second configuration file, which is used for the Eiger-based flow to prove the fairness and liveness properties. Yeah. And then for the last part, for the color statements, it's basically we have a configuration file for SMT PMC YIS to create traces that for all the cover statements, such that the cover statements are fulfilled, so you can take those traces, put it in the simulator and look at them and check if there is check at the simulation. In this case, it's also verifying that the assertions. Alright, so this is more or less a complete thing. Okay. The thing what Yosis or Symbiosis can do. What can we do else? Let's look at some memory example. So this is a simple memory with a transparent read. So transparent read is here, so meaning when you take the address, it directly puts that on the output. This is quite similar to the implementation of the memory of the eBooks core. Okay, so this memory has some write strobes. So this write strobe is a 4-bit input signal indicating which of the bytes of the 32-bit memory needs to be written. So this is actually very similar also to the eBooks core, which also has this byte enabled signal. So this write strobe or byte enable indicates which byte of 32-bit memory needs to be written. Alright, so this looks like a straightforward implementation of some memory. But now let's look at that memory. Basically, this is a different implementation of the same memory, behavior, hopefully. But as you see on this lines of code, it's a little bit more complicated. But sometimes you really have to stick to certain style of writing the code, such that the synthesis tool catches this to use the correct underlying memory elements for that. So sometimes you have to write that more complicated style of a memory, such as, for example, the FPGA synthesis tool uses or takes the correct memory blocks for that. Yeah, but when you write that code, you maybe are not that exactly sure if this is equivalent to the memory you started with, so the memory implementation, the simple memory implementation we had before. Yeah, so you're not sure maybe if you broke your design. And now you can use Symbiosis to create a proof that both designs are functionally equivalent. So basically what you do is you create a top-level design memcomp compare, for example, with a lot of primary inputs, and in that you create two instances of the memory. The first one is the simple memory, and the second one is the more complicated memory. Since they both are implementing the same behavior, they also have the same input. So you connect all the same inputs, and then you have two different outputs, one read data for the first memory and one read data for the memory. Now you can create a specification for that. So the specification can be embedded to the Verilog code, or it can be written as an external file in SMT lib code. And here you create basically an initial statement, an initial assumption on the system, and then your assertion. The initial assumption is that both memory elements, the memory elements of memory 1 and the memory elements of memory 2, they are equal. So this is this equal. So the initial state of both memories is that they both have the same contents. And then you create your assertions. The first assertion is that the memory elements of both memories, they will stay the same all the time, forever and always. So whenever you write something, this goes into both memories, and you always read the same data, RData1 and RData2. And then you have basically a symbiosis script to read all the files, and it creates, or it tries to create a proof that both memory elements are the same. Yeah. And if this proof succeeds, then this means that both memory elements implement the same behavior, and you are sure that memory 2, which is more complicated in terms of Verilog code, is really the exact same behavior as memory 1. So this is actually quite some simple use of symbiosis and on how to use formal verification as a designer. Right. So now let's look at some a little bit more serious. Let's look at RISC-V formal. So RISC-V formal is basically, it's a framework that allows you to do end-to-end formal verification of a RISC-V processor against a formal verification, a formal specification of the RISC-V specification. So you implement your RISC-V core, you have a RISC-V specification, you have a formal RISC-V specification, and then RISC-V formal allows you to verify that the behavior of your RISC-V core corresponds to the formal specification of RISC-V. So yeah, your RISC-V, you already know that, maybe. So RISC-V is an open instruction set architecture. Yeah, it can freely be used for any purpose. The EBEX core is a RISC-V core, and of course there are many different implementations available from different vendors with different microarchitectures, small designs, large designs. Yeah. But what's important here is that to have RISC-V as one of the succeeding instruction set architectures is that all those implementations, that they are compatible, that the same compiler can be used to compile programs for one or another implementation of RISC-V. So you really need to show that the implementation is correct according to the specification. So what you can do is, of course, of course, you can use a simulator to check whether the computation or the behavior of your RISC-V implementation corresponds to the specification. But sometimes this is not that easy to have a full simulation of all the edge cases, for example. But there may be some bugs in your design or you do not cover in your simulation. But RISC-V formal here can really help you with that and can verify the correctness of the implementation. So, what is end-to-end verification first? Well, historically, most of the checkable safety properties, they were just small properties of the system. So they are just verifying, for example, one signal under a certain condition. And then the engineers need to make sure that all the small properties in total, they ensure the correct functionality of the design. In end-to-end verification, on the other hand, we describe the whole functionality and we want to prove the whole functionality of the design. Of course, there are many pros and cons for that. And this example allows you, and one pro example for that is that when having this end-to-end verification, you can port the specification from one implementation to another, because in the end the other implementation, the other RISC-V core should of course implement the same behavior. So you can take the whole specification and not the very detailed specification and put that to the other core. Because the specification itself is complete, is self-complete, and does not depend on the actual implementation of the design. But of course, these pros, they also have some cons, and one of this is those large proofs, they are computationally quite intensive, and sometimes it's even not possible to have the full end-to-end verification. But with recent improvements in the technologies of solvers, we can start thinking about dealing with that problem and to really have end-to-end verification again. All right. And for RISC-V, we basically have RISC-V formal, which is basically one key example where end-to-end verification works for really large designs. So RISC-V formal is not a formally verified processor. Instead, if you have a RISC-V processor like the EPEX core, you can use RISC-V formal for that processor and confirm that the processor matches the specification of RISC-V. For some parts, it is using bounded methods, so bounded model checks. Theoretically, you could also use unbounded proofs with RISC-V formal, but that's not the main use case here. What is really useful is bug hunting. For example, the RISC-V formal creates you RISC-V formal creates you a trace, a counterexample, telling you that the processor can diverge from the desired behavior after 1,000 or 5,000 cycles. But usually, when you have a processor and you can't reach a bad state within a very short amount of cycles, you already have high confidence that your processor implements the ISA correctly. So if you have a process and would like to integrate RISC-V formal, you need to do two things. The first thing is you need to create or implement a special trace port. This is called the RISC-V formal interface, RVFI. And this is basically to allow the solver to observe the state of the processor in the same way for different implementations. So this interface is the same for all processors. And then of course you need to configure RISC-V to know about the features of your processor, because RISC-V has quite some options, what it implements, what it does not implement. So you have to configure RISC-V formal telling you exactly what features are supported by your processor, and then it can be used to verify the design. Actually, RISC-V formal, the specification of RISC-V formal also, the specification itself is also formally verified against a different specification, a different implementation of the specification, let's say it like that. In this case it's called RISC-V semantics, which is nowadays the official formal specification of RISC-V written in Haskell. So there's a formal proof also that the specification of RISC-V formal, which we'll see in a few slides, this specification matches the specification of RISC-V semantics. Alright. Yeah. These are currently the supported modes of RISC-V, so there's 32-bit and 64-bit, etc. Alright, so how does the environment of RISC-V formal look like? Well, in the middle we have our RISC-V core. This is, for example, now the EBEX core. This is the processor we want to verify with RISC formal. And then this processor communicates with memory and I/O. This is basically in a test bench. However, those elements, they are abstractions. So there's no full memory and no full I/O implementation in the test bench. Instead, we have a formal abstraction of that. And then we have this RISC-V formal interface here. So this is our trace port on which the proofs are looking for to observe the inner state of the processor. So this is basically the observable state of the processor that also the instructions have access to. So what do we need to implement for that RISC-V formal interface, and how does it look like? So whenever the processor retires an instruction, the RISC-V formal interface documents which instruction was retired. So it tells us this is the instruction word I, this is the reduction word I just retired. This was the program counter where I found this instruction. This is the program counter of the next instruction. These are the registers I read. These are the values I observed in the register file. And this is the value I've written to the register file. All that stuff. In short, with this RISC-V formal interface, we document basically the state of the processor that is observed or used by an instruction, and that is changed also by the instructor. with processors nowadays, for simple processors, it's like that. So a simple processor retires one instruction per clock cycle, and we're done. Yeah. But nowadays we have also more complex processors like superscalar processors, but also smaller processors. So non-superscalar processors, they can retire instructions. They can retire multiple instructions in parallel. So it can, for example, retire an instruction to memory and then one instruction to the register file in parallel. So this also needs to be covered in the formal interface. And for that, this formal interface is basically expanded to multiple channels, to the amount of channels the processor can, so that the processor can retire all the instructions in parallel. So for all instructions that the processor can retire in parallel, there's one full channel of the RISC-V formal interface, and this is done with a parameter. So you need to configure that with in the configuration. With this nRed parameter. So you have nRed amount of signals of the signal R, V, F, I valid, for example, and so on. So this is basically the number of channels for the formal interfaces, for the number of instructions the processor can retire in parallel. Yeah, so those are the signals, and then you have those are the signals for the formal interface, and there you have signals like what register file address you are accessing, what data you are accessing, what are memory addresses, what are the register values and addresses you are going to write, etc. Okay, so now let's say we have a processor that is implementing that interface. So what is the verification strategy now that RISC-V formal follows in order to do the proof and show that the process is actually correct? So one thing you need to understand here is that there is not just one single proof. Instead, there is a large number of very small proofs we run, and this is the most important trick when it comes to end-to-end verification. We split up one large proof and divide it to many small proofs where we can deal with the complexity. So basically we have two categories of proofs here. One category is called the instruction checks. We have those proofs for every instructions in the specification of RISC-V, and for every channel also. So this easily gives you a couple of hundred proofs. So you easily have 100 instructions, and then you have like two channels. Then you already have 200 proofs that you have to run. And what the instruction checks do is they basically reset the processor or start at a certain symbolic state, and if you like to run an unbounded proof, then let the processor run for a certain number of cycles, and then in the last cycle it will retire a certain instruction. And if this check, for example, if this check checks that an add instruction works correctly, it assumes that the last instruction that the processor will retire is an add instruction. And then it looks at all the interfaces of the RISC-V formal interface to make sure that the behavior of the add instruction is compliant with the specification of the add instruction. It checks if the instruction was successfully decoded. It checks if the register values we write is actually the sum of the values we read from the register file, and all that stuff. But if the register values we write, but when we're doing these checks, if we just run these instruction checks, there's still a small verification gap, because the processor might lie to us. The core might say we write this value to the register file, but then it does not update the register file internally. So for this, to prove that this is actually not the case, we have to have a set of separate proofs. This does not look at the entire RISC-V formal interface, but only in one. So this set of proofs does not look at the entire RISC-V formal interface in one clock cycle in the end, but instead it looks at a fraction of signals, but then over a span of cycles. So for example, the check says if I write a register, a certain register, like for example X5, and then when I later read the register back, then I need to get back the value I've just written before. And those are called the consistency checks. So with these both types of proofs, we can get a full verification of a core. So how does the specification look like? So for the instruction checks, so I already had that before. So for the instruction checks, so there are two slides for that. For the instruction checks, we have a couple of interfaces of signals going in and out. So this is basically the RISC-V formal interface we are looking at. And then we have the implementation of that. What's interesting here is that the specification of this instruction is completely written in Verilog. So you have the input body, or the module interface, and then you have the internal implementation of the check. So internally we have different parts. The first part here is basically the decode part, where we take the observed instruction and then decode that to the internal signals. Then we have the behavior, like the result is the sum of the, if this is the sum of the register and some immediate coming from the instruction, and so on. All right. And then we also have the certain parts of the specification. Those are basically output signal of the check. Like for example, which registers should be read, which registers should be write, which value should we write, and so on. So that's the interface, and this is basically done, this is done for all the instructions we have. We have in the RISC-V specification. Okay. Yeah. So we also had that before for the consistency check. So the consistency checks, they do not look at all signals at once. Instead, they look for a certain number, fraction of signals, and then look for them for a span of time. So where do we have consistency checks? So there are consistency checks, for example, for the program counter for one instruction. So I have, for example, instructions that says this is the program counter, and then this is the program counter for the next instruction. And then we can take a look at the next instruction and look if the program counter is actually the next instruction of the previous instruction. So they must link together. Yeah. So this is done basically in both directions because of when a processor might retire multiple instructions in parallel. So you need to have that here in both directions. There is also one check that looks if the processor is alive, like giving the processor some fairness properties. For example, if you do a memory access, then you will always get a memory access after a few cycles and so on. So what can you do with that? What bugs can you find with RISC-V formal? Actually, that's not an easy question because you cannot give a complete list on that. It can definitely find incorrect implementation of a single-threaded semantic of your RISC-V instruction. So if you implemented your instruction differently or incorrectly in your code, then RISC-V formal will find that. It can also find a lot of bugs in pipelining. When you do forwarding and bypassing of certain stages, or you have to pipeline interlocks and so on. It can find bugs related to reordering, where you, for example, reorder an instruction which you should not do. It can find freezes, or it can find bugs related to memory interface. But that depends on things like sizes of the cache lines and so on. What RISC-V formal currently not can do is it cannot find stuff which is not covered by the RISC-V formal interface or by the specification, like for example control and status registers and extensions of the instruction set architecture like floating point and so on. And also RISC-V formal has currently no support for so-called hearts. So RISC-V allows you to implement basically different ALUs in parallel, or different hearts as they called in RISC-V, and this is not covered yet. So anything that is not covered by specification cannot be found with RISC-V formal. So what has RISC-V formal found already? Well, RISC-V formal actually has found bugs in many designs. It found bugs in Spike. Spike is the official instruction set simulator of RISC-V. It found a bug actually in the ISA specification of RISC-V. So this was not precisely specified there and led to a bug. And it found bugs in many different RISC-V implementations. Also the EBEX core. The EBEX core is also formally verified using with RISC-V formula. So what bugs does it typically find? One classic bug it found is, for example, clearing the LSB of the addition result of a jumbled link register instruction, which is currently still specified, but I think this is going to be removed from the official RISC-V specification. And also bugs related to resets, weird timings in the pipeline stages and so on. But the nice thing here is really that when it proves you, it gives you proof that your design is not correct, it creates you a trace, a VCD trace or a complete Verilog test bench that you can instantiate and implement and run on your simulator to understand what is going on in your core, because sometimes it's not easy to understand what the processor is doing when giving you a counterexample and so on. Alright, so finally I wanted to talk a little bit about the insights of RISC-V formal, and in particular about cut points, black points, and other abstractions, so that you have a little bit of an understanding on how RISC-V can deal with the complexity. So the idea behind abstractions in RISC-V formal or in formal methods in general is that you switch out parts of the design with a different circuit that is less constrained. It still includes the original. It still includes the behavior of the original circuit, but it might do some other stuff as well. The textbook example here would be a counter. Usually the counter would just increment in steps by one. One abstraction could be that I create a counter that can also skip numbers. It will just increment strictly in steps, but it can skip numbers. But this, it can, it must not. It can, but yeah, it must not. This still includes the behavior of the original design, but it's less constrained. So if I can prove a property with the abstraction in place, instead of the increment by one counter, we have proven that an even stronger property that includes the same property of the original design. And the idea of abstraction actually works very well with RISC-V formula. So the main reason why we do this in RISC-V formula is that it leads to easier proofs. For example, with black boxes. For example, consider an instruction checker that just checks if the core implements the add instruction correctly. For this checker, we actually don't need a register file that is working. We could simply replace the register file with something that ignores all writes to it. And whenever we read something from the register, it will return an arbitrary number. That would still include the behavior of a core with a functional register file, but because the instruction checker doesn't care about the consistency of the register file, of the writes and reads, we can use that abstract register file that just returns random numbers. We can do that because we already know that we have different proof that explicitly checks for consistency of the register file. And with that idea, it is possible to abstract large parts of the process away, and therefore it yields to much easier proofs. Depending on what solver we are using, the solvers themselves, they are already capable of finding those abstractions themselves. So in this case it does not really help by adding those abstractions manually, but just realizing that the potential for these abstractions is there is very helpful when guiding your decisions how to split a large verification problem into a smaller problem that you can actually solve. Yeah. So let's continue with bounded model checks. Here it's always the question: what bounds should we use? How many steps should we use for the verification? Of course, a larger bound is better, but on the other hand, it also yields to proof that is much harder to compute. But if you have a small bound, you have something that runs very quickly, but you are maybe not very confident that it has proven something that is relevant to you. In practice, there are two solutions to deal with the problems. The first solution is that you can use the same solver to cover certain events. For example, you can write something saying you would like to solve you would like to see, for example, a memory read and write and at least one instruction for the ALU. And then you can ask the solver what is the shortest trace that would satisfy all this stuff. And then you maybe get a trace of let's say 30 clock cycles. And then you know that if you look at a proof with, that is 30 clock cycles deep, then at least there are cases like this memory read and write and ALU operation. This is covered. And the second part, maybe it's even more important, is that when you write a processor, you typically find bugs already, not just with formal verification, but during the development of the code with just simulation. And one thing here is that you do not just simply fix the bugs, but and forget about them, but instead let's say you preserve them in a way that you can reintroduce the bug later when you finished your design. So when you finish your design, you maybe introduce the bug again, and then you can look at if RISC-Formal proves you that your design is not correct because you've introduced the bugs, obviously. And if you have a couple of those bugs possible for later reintroduction, then you can easily find a bound that is sufficiently large enough that you have a high degree of confidence that very similar bugs can also be found by the formal verification. All right, so with that, let me come to a short conclusion of a very small introduction to formal verification of hardware designs. So essentially, formal verification is another tool. Let's say it like this: it's another tool in your tool belt, helping you to build correct designs. And this should be something for the designers and not just for guys specialized for formal verification. As you've seen, maybe in the examples and also with RISC-V formal, it's not always about proving the full correctness of the design. Instead, formal methods can be used for bug hunting as well. They can be used for small designs like counters or arbitrary other designs, but they can be also used to prove the correctness of quite some large designs like a full RISC-V processor. Important to say is that you do not need to formally verify the whole design. Instead, it's always very easy or very helpful to just prove the correctness of just parts of the designs, like having just a partial specification of design can help you to find quite some large classes of bugs. And the keyboard to deal with all the complexity, of course, is abstraction, as you've seen just a few slides ago. So if you want to play with that, those tools, they are all open source, so they are available on GitHub. You can download them and can apply them also to your designs if you like. Alright, so with that, I'm now at the end of this lecture. Are there any questions regarding formal verification? Because if not, I will just close the streaming session here, and then we will continue with the question hour on Discord. So if you have questions regarding to your practicals, yeah, just be in the Discord channel and ping us, and we will discuss your questions either in public or in a private session. So I'll be there, but also Pascal will be there, and I'll be there just in a few minutes when I'm back in the office.